For more than a century, scientists believed they understood the monster sleeping beneath Yellowstone, a colossal chamber of molten rock, sitting quietly under the crust, slowly filling with pressure like a bomb on a very long fuse. That was the story taught in classrooms, repeated in documentaries, and whispered about every time the ground so much as trembled in the park. But in the last year, two separate teams of scientists looked closer than anyone ever had before, and what they found does not just add a new detail to that old story. It rewrites almost everything about how Yellowstone actually works, where its magma truly comes from, and why the world's most famous supervolcano has not erupted in more than 600,000 years. Let's start with the discovery that finally answered a question geologists have argued about for decades. Where exactly does Yellowstone's magma system begin? A team of researchers from Rice University, the University of New Mexico, the University of Utah, and the University of Texas at Dallas set out to find the precise boundary, the exact depth where solid rock gives way to the molten world below. Their method was almost shockingly physical for something this scientific. They drove a 53,000-pound Vibrosis truck across the caldera, a machine that sends controlled vibrations deep into the earth, essentially thumping the ground like a drum and listening to the echo. More than 600 seismic sensors captured those echoes, building one of the most clearest pictures ever created of what lies beneath Yellowstone's surface. What they found was a sharp, gas-rich cap sitting about 3.8 kilometers, or 2.4 miles, beneath the northeastern part of the caldera. This is not molten rock in the traditional sense. It is a strange, partly melted layer laced with bubbles of supercritical water, sitting directly above the magma system like a lid on a pot. And the crucial detail, the one that changes everything, is that this lid is not sealed shut. It is only slightly porous, which means it does not trap pressure until the system violently fails. Instead, it lets gas escape slowly and constantly, venting upward through Yellowstone's famous geysers, its bubbling hot springs, and its steaming fumaroles. Researchers compare it to steady breathing, small, continuous belches of gas escaping through thousands of tiny vents scattered across the park, instead of one massive buildup with nowhere to go. That single mechanism may be the reason Yellowstone has stayed quiet for so long, even while sitting on top of a magma reservoir that has existed for roughly 2 million years. The system is not sealed, it is breathing. And a system that breathes efficiently, releasing pressure in a slow, steady rhythm, is far less likely to explosively fail all at once. To be absolutely clear, this discovery does not mean Yellowstone is dead or dormant in any permanent sense. The magma sitting beneath that lid is largely rhyolite, the same explosive type of magma responsible for the supervolcano's 2 previous supereruptions. The researchers describe it best. This is a sleeping giant, not an extinct one. What has changed is not the danger itself, but scientists' understanding of why that danger has stayed contained for so long, and that understanding gives them a far sharper baseline for detecting any future change in behavior. But that was only the first discovery. Almost at the same time, a completely different team, this one from the Institute of Geology and Geophysics at the Chinese Academy of Sciences, was tackling an even bigger mystery, not just where Yellowstone's lid sits, but where all of its magma actually comes from in the first place. And their answer overturned one of the most widely taught ideas in modern geology. For decades, the leading explanation for Yellowstone was something called a mantle plume, the idea that a narrow column of superheated rock rises like a blowtorch from deep near Earth's core, all the way up through the mantle, feeding the volcanic system from below. It is a dramatic image, and it has appeared in textbooks and documentaries for years, but using a highly detailed 3-dimensional model simulating the actual behavior of the crust and mantle beneath. Western North America, researchers found something entirely different is going on. Instead of a deep vertical plume punching straight up from the core, the real driver appears to be something researchers are calling a mantle wind, a broad, horizontal flow of hot rock moving slowly eastward through the shallow mantle, not from the depths of the planet, but from something much closer to the surface, remnants of an ancient tectonic plate called the Farallon Plate, which has been sinking and dissolving beneath North America for millions of years. As this hot material drifts eastward and encounters the thick, deep root of the continent sitting east of Yellowstone, it gets pulled downward and stretched. That stretching triggers something called decompression, melting, the same basic process that generates magma at mid-ocean ridges, and it is happening directly beneath the park. At the same time, buoyant material to the west is pushing back in the opposite direction. These two competing forces are essentially tearing the base of the continent apart in a very specific pattern, creating a long southwest tilting channel underground. That channel acts like a highway, allowing magma to rise, accumulate, and evolve over enormous stretches of time, shaping the very structure of Yellowstone's underground magma system as it currently exists. Think about how significant this shift really is. For generations, the assumption was that Yellowstone sits above a fixed hotspot, a plume rising from the deepest layers of the planet, largely disconnected from the tectonic plates moving above it. That is the model still repeated in countless articles and classroom lessons today. This new research suggests the truth is almost the opposite. Yellowstone's fuel supply is deeply tied to the ongoing active tectonic history of North America itself, connected to a vanished ocean plate that has been quietly reshaping the continent from below for tens of millions of years. To understand why these two discoveries matter so much, it helps to remember exactly what Yellowstone has done in the past. Over the last 2.1 million years, this single volcanic system has produced two super eruptions, events so massive they release more than 1,000 cubic kilometers of magma, rock, and ash in a single event. To put that into perspective, that is roughly 1,000 times more material than typical large volcanic eruptions release. Events on that scale do not just devastate the immediate region. They can inject enough ash and gas into the atmosphere to alter climate patterns across the entire planet for years afterward, disrupting agriculture, ecosystems, and human societies on a global scale. For a long time, the working theory behind supervolcanoes assumed something relatively simple. A single, large chamber of liquid magma sits beneath the surface, filling gradually with molten rock until the pressure eventually becomes too great for the surrounding rock to contain, at which point it fractures, collapses, and erupts catastrophically. It is an intuitive model, almost like a balloon slowly filling with air until it bursts. But growing evidence over recent years suggested that picture was far too simple, and increasingly, scientists suspect that active supervolcanoes do not actually store magma this way at all. Instead, the real structure appears to be something researchers call a magma mush system, a vast, partially molten zone that can extend through much of the crust and upper mantle rather than a single concentrated chamber waiting to explode. These mush systems behave very differently from a simple liquid reservoir. They are thick, sluggish, and far less mobile, which raised an obvious question that puzzled geologists for years. If magma beneath supervolcanoes is spread out and mostly solid rather than liquid, how does a system like that ever generate the kind of massive, fast-moving eruption capable of producing a super eruption in the first place? That is precisely the puzzle these two new studies, arriving within months of each other, finally began to solve. The Vibroseis survey revealed how the system manages its pressure on a day-to-day basis, breathing steadily through a porous cap rather than sealing everything inside. The mantle wind model revealed where the raw material feeding that entire mush system originates and how it continues to be replenished over enormous stretches of geological time. Individually, each study answered a piece of the puzzle that had remained stubbornly unclear for years. Together, they form the most complete physical explanation scientists have ever had for how a system like Yellowstone actually functions, from its deepest fuel source all the way up to the geysers steaming across the surface. One explains why pressure has not been building toward catastrophe, despite an enormous, long-lived magma reservoir sitting almost directly beneath Old Faithful. The other explains where all of that magma is actually coming from, and why the system has remained active for millions of years instead of fading out like so many other ancient volcanic centers. If you are the kind of person who wants to understand what is really happening beneath the ground instead of just the scary headlines, go ahead and hit like on this video and subscribe. Because breaking down real research like this, in plain language, is exactly what this channel is built around. None of this means the danger at Yellowstone has disappeared. No scientist involved in either study is claiming that. What it means is that researchers finally have a far more accurate map of the machine itself, how it breathes, where its fuel comes from, and how those two systems connect underground. Before these discoveries, scientists were essentially working with an incomplete blueprint, guessing at connections between processes they could not directly observe. Now, for the first time, there is a detailed, physically grounded model tying the mantle, wind, the tearing continental root, the rising magma channel, and the breathing lid together into one coherent picture. That kind of clarity matters enormously for monitoring. Knowing exactly how deep the cap sits, and understanding that its slow gas release is a stabilizing feature rather than a warning sign, gives researchers a genuine baseline. If that behavior ever changes, if the porous lid begins sealing instead of venting, or if the mantle wind driving fresh material toward the surface shifts in some unexpected way, scientists will actually be equipped to recognize it as a meaningful deviation instead of just background noise. It also reframes how scientists think about supervolcanoes far beyond just Yellowstone. If this same combination, a breathing pressure release system layered above a mantle, wind-fed magma highway, turns out to be common at other giant volcanic centers around the world, it could change how researchers monitor dozens of similarly dangerous systems, from Japan to New Zealand to the volcanic fields of South America. A framework that finally connects deep tectonic history to shallow, observable behavior at the surface gives volcanologists a genuinely new tool, not just for Yellowstone, but for understanding the broader family of Earth's most powerful volcanic systems. It is also worth remembering just how differently these two research teams approach the same underlying mystery. One team worked from the top down, physically sending vibrations into the ground and mapping the shallow structure with unprecedented precision. The other worked from the bottom up, modeling the deep, slow, moving currents of mantle rock that have been shaping the North American continent for tens of millions of years. Neither approach alone could have produced this level of understanding. It took both perspectives, meeting in the middle, to finally connect the dots between where Yellowstone's magma originates and how the system manages to stay so remarkably stable on the surface. For now, the picture that emerges is almost reassuring in its complexity. Yellowstone is not a simple bomb quietly filling with pressure underground. It is an enormous, deeply connected system, tied into the slow tectonic churn of an entire continent, breathing steadily through thousands of small vents instead of holding everything in until it cannot anymore. The supervolcano beneath. America's oldest national park is very much alive, still fed by forces reaching back tens of millions of years. And for the very first time, scientists finally understand how and why it has stayed calm for so long.